James Webb saw something that didn't quite fit the description of a space object, a warm stripe, a thin, stretched band of heat, sitting on the night side of the object, not the sunlit side, not the, yeah, it's warming up side, the side that should be dead, frozen, black, the side that should be radiating almost nothing except the cold memory of the universe. So the question isn't, is 3I Atlas active? The question is, why is it warm where sunlight can't reach? And why does the pattern look deliberate? Because this wasn't a messy glow. It wasn't a scattered patch. It wasn't maybe a dusty reflection. It looked like a mark, like a scar of heat dragged across the surface, too smooth, too continuous, too clean to be a random hot pebble. And NASA didn't run headlines saying, "We found a heater in space." Of course they didn't. The official word stayed careful and boring, but the instruments don't speak boring. Infrared doesn't care about public messaging, it only cares about energy, and it saw energy where it shouldn't exist. Let me slow it down, because this part matters. JWST doesn't see like your eyes. It reads heat signatures like a thermal camera pointed at the universe. If something is warmer, it glows more in infrared. Even if it's dark, even if it's far, even if it's trying to hide behind dust and distance. So when Webb stared at 3I Atlas, it wasn't looking for a pretty tail. It was looking for temperature structure. And what it found was not a comet vibe. It found a thermal gradient that looked like a stripe, like something was warming a line across the body, on the side facing away from the sun. That's like finding a campfire, burning on the back of a mountain that hasn't seen daylight in weeks, with no lightning, no people, no reason. And the first explanation people threw out was rotation. The idea that maybe the stripe was just a sunlit region turning into view, but that excuse collapses fast because the stripe didn't behave like leftover sunlight. It stayed too stable in shape, and it showed up where cooling should win. A simple rock spinning in space doesn't keep a clean, warm band on its night side. It cools evenly, it fades, it smears out. This didn't smear. So the next explanation was outgassing. Maybe a jet of gas is blasting out, carrying warmer material, or exposing fresh subsurface ice. That's closer. But here's the problem. Outgassing jets on comets are usually chaotic, like cracks screaming in random places. They don't paint clean stripes, they don't draw a line and hold it like a signature. And if the stripe is from a jet, it means the jet is active on the night side, meaning something is powering it without sunlight. Now you're trapped in the real nightmare logic. If it's not sunlight, then the heat must come from inside, or from an interaction with space itself. Inside heat is rare for a small, icy body. Space rocks aren't supposed to have engines. They aren't supposed to have stable internal warmth. They're supposed to be leftovers, frozen debris, ancient dust piles with no pulse. So when Webb shows warmth on the dark side, you're forced to ask something nobody likes asking out loud. What kind of object stays warm in the cold? What kind of object maintains structure while traveling between stars? And why does the warm band look like it was placed, not formed? Because the stripe wasn't centered like a natural core heat leak. It was offset, skewed, like it followed a path across the surface. Not heat escaping everywhere, more like heat routed through here. Now zoom out for a second because the timing makes this worse. The warm stripe appeared during a period when 3I Atlas was already under intense tracking. Webb, ground telescopes, NASA's DSN timing, follow-up imaging, everyone watching the same moving dot from different angles. And across that window, the stripe behaved like a feature, not a fluke. It repeated in the data. It held its position relative to the body. That's why this isn't a one-frame ghost. This is the kind of thing that survives cross-checks. And here's what makes the nightside detail so lethal. Nightside means the surface is radiating away heat into space with no replacement. If the stripe remains warmer than expected, something is replacing the heat fast enough to compete with deep space cooling. That is not a little weird. That is a power problem, a supply problem. So what supplies it? The soft explanation is chemistry. Certain ices can react. Certain trapped gases can release energy when cracks open. Phase changes can generate heat, but those processes tend to be messy and short. They erupt, they fade, they don't write thin stripes like someone used a brush. Another explanation is friction, micro impacts. Dust hitting the surface and heating a line where material is being scraped. But impacts don't choose nightside, and they don't repeat on schedule unless something is steering the environment around the object. Then comes the one explanation that always sits in the back of the room, unspoken, because it scares people into silence. Control. Not magic, not aliens, just the concept of an object that can manage its own thermal state in a way natural debris usually can't. A system that can heat one region while leaving others cold because it wants a gradient, or because it needs it. And if that idea feels too extreme, here's the calm version that still terrifies me. Even if it's natural, even if it's internal, it implies 3I Atlas isn't a dead rock. It's a structured body with active layers. It's not just drifting, it's doing something, and once you admit that, Everything we've been treating as a space weather coincidence starts feeling like it belongs to the same story. Because warmth isn't just warmth. Warmth can mean pressure. Pressure can mean jets. Jets can mean course nudges. And course nudges are exactly the thing everyone keeps trying to avoid saying about 3i Atlas. So the stripe is more than a thermal oddity. It's a clue to mechanics, to behavior, to capability. If Webb is right, then 3i Atlas isn't only reflecting sunlight. It's producing its own signature. And in deep space, anything that produces its own signature is not passive. It's participating. Now you probably want the most important question answered next. How warm was it, really? Warm enough to matter, or warm enough to just be a rounding error on a scientist's spreadsheet? That's where the story gets sharp, because Webb isn't guessing. It measures temperature differences that are small but meaningful in a place this cold. A tiny rise out there is a flare. A whisper becomes a siren because the baseline is near silence. So even a narrow band that's only slightly warmer stands out like a glowing wire in a dark room. And it doesn't just stand out visually, it changes what the object can do physically. Warmer areas outgas sooner, warmer areas crack easier, warmer areas shed material faster, warmer areas respond quicker. So a warm stripe is a steering wheel disguised as a detail. Now let's talk about why that warm stripe is such a problem, because it's not just a little hotter. It breaks the simple physics story people want to tell. In comet logic, sunlight hits the day side, heat creeps through the surface, and the night side cools off fast into black. That's the rule that keeps things sane. So when JWST sees a structured warm band on the dark side, the first defense is always the same excuse: rotation, geometry, and a misleading viewing angle. And yes, rotation can fake things sometimes. A sunlit patch can swing into view, and your brain can mistake just cross the terminator for night side. But the stripe didn't behave like a patch that just rotated out of sunlight. It held its form too cleanly, like it was anchored, not drifting with cooling. Cooling is messy. It doesn't keep sharp edges. It fades unevenly and smears into a gradient. A stable stripe means something is feeding it, even softly. So the next defense is thermal inertia. The idea that rock and dust can store heat, then release it slowly, keeping a region warm after sunset. That's real, but here's the catch. Thermal inertia makes broad, gentle warmth. It doesn't draw a narrow band like a brush stroke across a rotating body. A stripe implies structure under the surface, like a layer or seam that conducts heat differently, or a region where material behaves unlike the rest. Now you might think, okay, it's layered. So what? But layered objects don't automatically heat their own night side in deep space. Layering explains why heat moves differently, but it doesn't explain where the heat comes from once the sunlight is gone and the surface is dumping energy outward. That's why outgassing becomes the next suspect. If a jet is active, the gas can carry energy and expose fresh material, creating a warmer patch in infrared. But jets usually leave chaotic fingerprints. They flare, they sputter, they migrate. They don't hold a clean stripe unless the vent geometry is stable. Stable vent geometry means a stable internal plumbing, cracks that stay open, pressure that stays available, and a supply that doesn't die immediately. And if the supply doesn't die immediately on the night side, then it isn't powered by the sun in the moment. It's powered by stored pressure or internal energy. That's the point where people start getting nervous, because stored pressure sounds harmless until you remember pressure can push mass, and push can alter motion. Comets show non-gravitational effects all the time, tiny accelerations from outgassing, but those pushes usually correlate with the sunlit hemisphere. A night side push is different. It can act like a directional thruster because it can fire when the day side is quiet, creating a torque and a net change. And torque matters more than people think. You don't need a rocket engine to steer if you can control when and where you vent, even a little. So the stripe isn't just a temperature anomaly, it's a control surface disguised as heat, because the warm band could mark the region where venting is managed. Now, JWST doesn't just look once and guess. It builds a thermal map across wavelengths, and different wavelengths tell different parts of the story. If the stripe is truly warm material, the signature should track like heat. If it's dust reflecting light, the signature shifts differently with wavelength. That's why the "it's just reflective dust" argument doesn't save you. A reflection can fake brightness, but it struggles to fake temperature across the bands. And remember, the stripe sits on the wrong side of the object. Reflection needs geometry, heat needs energy. Geometry can trick you, energy must be supplied, so NASA teams do what they always do. They run models, they simulate spin rate, shape, thermal inertia, roughness, and they see what kind of night glow is normal. Those models can explain a faint warm shoulder near the terminator, they can explain delayed cooling, they can explain broad smears. But a narrow stripe that stays coherent is harder, because coherence means the surface is not uniform and the heating is not random. Now add one more uncomfortable layer. A stripe isn't just warmth. It can be frictional heating from material sliding, grinding, or shedding in a controlled line. If 3i Atlas is releasing dust along a seam, that seam could heat like a brake pad. Tiny energy, but enough to stand out in deep space cold. A seam suggests construction in the geological sense, a contact boundary between layers, or a fault line that's been stressed and reopened repeatedly. But why would an interstellar body keep a seam active now, in our system, at this time, with a pattern that appears when we're watching it hardest? That's why some people quietly considered an uglier possibility. Not science fiction, but simply an object that is mechanically more organized than typical debris. Organized doesn't have to mean artificial. It can mean unusually dense, unusually stratified, unusually sealed like a capsule that preserved internal volatiles too well. If it preserved volatiles too well, then warming anywhere can unlock pressure that has been trapped for ages, and trapped pressure doesn't behave politely. It can vent through the path of least resistance, and if the least resistance is a long crack, you get a line source, not a point source. A line source is exactly how you draw a stripe in thermal data, because the energy is distributed along the crack, not concentrated at one vent hole. Now listen carefully, because this is where the story turns. If the stripe is a line vent, then the object can vent while keeping most of its mass stable. That means it can release gas without shredding itself, like a controlled bleed instead of an explosive outburst, and controlled bleed is efficient for steering. This is why the "just a comet" label starts to sound lazy. A normal comet is messy. It spins, it cracks, it flares. It does not look engineered by accident. But 3i Atlas keeps showing traits that feel optimized. A warm band in the wrong place, a clean signature, a stability that refuses to collapse into noise, and the timing is the salt in the wound. Because the stripe shows up during the same observational windows when orbit solutions get revised. It's never, nothing changes, everything is normal. It's always a small anomaly appears, then models adjust, then we move on fast. Now you probably want to know the one thing that turns this from curiosity into threat. Could that stripe be enough to change the trajectory? Not by a huge amount, not by Hollywood levels, but by a measurable amount over time, the kind that makes predictions drift until you need a new explanation. That's what non-gravitational acceleration does. It's tiny per second, but it accumulates, and accumulation is how small forces become large consequences. So the real fear is simple. If the stripe is a controlled vent seam, then 3i Atlas may be capable of choosing when its natural pushes happen. And if it can choose timing, then it can choose geometry. And if it can choose geometry, then it can make its path look accidental while staying precise. That's not a claim of intent, it's a claim of capability. And capability is the only thing you need to make scientists lose sleep, because once you find a mechanism that can steer without engines, you can no longer dismiss every trajectory tweak as measurement noise. Now here's the moment the worm stripe stopped being a Webb oddity and turned into a NASA problem, because the first thing they did was ask one brutal question: can anyone else see it? Because JWST is powerful, but it's also a single set of eyes, and when you're staring into deep space, one set of eyes can be fooled by geometry. So NASA pulled in the usual: backup players, ground telescopes, older space assets, and the quiet teams who live inside the data pipeline at JPL. Not to chase a headline, but to kill the anomaly fast, because the fastest way to end panic is to prove the weird thing was a misread. But the stripe didn't die. When they compared Webb's infrared map to optical tracking, the object's brightness variations didn't match the simple, sunlit patch rotating story. The light curve said one thing, the heat map said another, and when those disagree, it means you're not looking at surface paint, you're looking at behavior. So they brought in Hubble observations, because Hubble can't see heat like Webb, but it can see the dust environment and any fine structure in the coma. If a night-side vent seam is real, Hubble should catch hints of asymmetric dust release, not huge tails, but a subtle bias in where particles drift. And that's exactly what the analysts hunted for. Not a dramatic plume, just a repeated imbalance in the coma geometry across different viewing angles. Meanwhile, ALMA entered the story for the molecular side, because if the stripe is venting, gas lines should whisper even when the optical view stays calm. ALMA doesn't care about pretty pictures, it cares about signatures, CO, CO2, anything volatile enough to move in deep cold. A clean thermal stripe plus a clean molecular signature is a bad combination, because it means you have both heat and mass flow aligned. Heat alone could be inertia, gas alone could be random leaks. Heat plus gas in the same geometry starts looking like plumbing. Then came the JPL orbit teams, because every physical theory has to face the same courtroom, the trajectory solution. And JPL doesn't do vibes, they do residuals. They fit gravitational models, then stare at what doesn't fit, the leftover drift, the tiny y that remains after the math is done. If the stripe is venting, the residuals should show a consistent push, small but biased in one direction relative to the spin state. And the scary part is that even a weak push can create a measurable arc over time, especially on a fast interstellar track. So they tried to bury it under uncertainty. Dust drag, background confusion, measurement scatter, anything that would inflate the error bars. But the error bars didn't inflate enough, because multiple stations watched 3i Atlas at different times, and the drift persisted in the same sign, like a whisper that kept repeating the same word. That's when the stripe became the leading suspect, because it was the only feature that could plausibly produce a directional effect without a visible engine. Now here's where it gets worse. NASA's Deep Space Network also watched the environment indirectly through timing stability. DSN isn't looking at the object's surface, it's measuring the medium, the delays, the tiny phase shifts that show when space itself gets strange. And during the same windows, Webb saw the stripe cleanest. DSN logs showed small timing quirks that didn't match normal space weather patterns. No giant solar flare, no obvious storm wall. Just a structured drift that made engineers squint and say, "That's odd," then move on. But odd becomes pattern once it repeats. So NASA started stacking timelines, Webb thermal pass, Hubble imaging, ALMA lines, DSN timing, JPL residuals. And when you stack them, the warm stripe sits at the intersection like a pin holding the whole map in place. That's why people stop calling it an artifact, because artifacts don't coordinate across instruments that don't even speak the same language. A camera artifact doesn't show up as a molecular line. A dust illusion doesn't show up as an orbit residual. A thermal stripe that survives all that is telling you something physical is happening. And the most uncomfortable detail is still the same, it's on the night side, which means it's not reacting, it's operating. If a comet only wakes when it faces the sun, you can predict it, you can model it, you can box it in. But if it can act in darkness, your predictions get soft. So the teams try to safer explanation, internal supervolatiles stored so well, they vent even without direct sunlight. That's plausible, but it still doesn't explain why the release looks like a line, not a scatter of random vents. Random vents make messy hotspots, a line vent makes a stripe, and a stripe implies a pathway. That pathway could be a crack, a seam, or a layered boundary acting like a conduit, channeling heat and gas along a preferred route. And if the conduit exists, it can produce something that behaves like a controlled thruster without needing anything you'd call technology. That's what makes this story so dangerous, because you don't need exotic explanations to get exotic consequences. You only need a mechanism that creates directional push. Now you probably expect NASA to publish a clean paper saying, "Nightside thermal band detected, likely vent seam." But that's not how it happens, not fast. First they talk in careful language. Anomalous thermal feature, asymmetric activity, non-gravitational effects consistent with outgassing. Words that sound harmless until you connect them. Because non-gravitational effects is the polite phrase for it moved when it shouldn't. And asymmetric activity is the polite phrase for it pushed itself in one direction. And anomalous thermal feature is the polite phrase for why is it warm in the dark. So when you hear those phrases, don't let them lull you. They're not boring. They're containment. They're how you say this is unsettling without starting a fire. Now, the real crosscheck wasn't just other telescopes, it was future prediction, whether the anomaly helps forecast the next deviation. If the stripe is tied to a spin phase, then deviations should peak at certain rotational orientations. So they began watching for rhythm, not in radio noise, but in residuals, tiny repeating bends that match the object's own cadence. That's the part that feels like a lock-picking exercise, because once you learn the cadence, you can predict when the object will push again. And if you can predict it, then the push is not random chaos, it's structured behavior, even if the cause is natural. So the story becomes a slow trap, because every new observation either kills the stripe or confirms it harder, and so far, it has only confirmed it. Which brings us to the most human moment in all of this, the one question the analysts keep circling without saying out loud. If 3i Atlas can maintain an active seam in darkness, how long can it do it, and what happens when it decides to do it closer in? Now here's where the warm stripe stops being a feature and starts acting like a timeline, because Webb didn't just see it once, it watched it change like something was adjusting. On the first clean pass, the band was thin and steady, almost polite. On the next pass, it looked slightly wider, like the heat spread along the same path on purpose. That alone could be geology, sure. But the widening didn't smear outward randomly, it expanded along the stripe's length like a line being activated section by section. And then, during a later window, the stripe appeared to kink. Just a small bend in the warm band, as if the conduit under the surface changed routing. That bend was subtle, but Webb's infrared mapping is ruthless. A tiny change in geometry becomes obvious when the background is so cold it barely emits anything. So NASA did what they always do next. They asked, is the stripe reacting to the sun, or is it reacting to the object's own internal cycle? Because if it tracks sunlight, it's boring physics. If it tracks internal cadence, then you're looking at something self-driven, even if the cause is natural. To test that, they started correlating the stripe's brightness with the rotation period inferred from optical light curves, the old school way to read a spinning body, and the correlation wasn't clean, which is the problem. The stripe didn't peak when the same surface faced the sun, it peaked when a specific phase returned. That means the trigger was not daylight, it was position, like a valve opening at a certain orientation, regardless of whether that side was lit. If you're a cautious scientist, you call that phase-linked activity. If you're honest, you admit it behaves like timing control. Then came a second change that made everyone sit up straighter. The stripe began to show a faint parallel band, like a ghost line running beside it. Not as bright, not as hot, but present. 2 lines means the pathway might be branching, or the surface is cracking in a way that repeats. A branching crack is not weird on a rock, but a branching crack that lights up in infrared on the night side in a stable geometry is much harder to dismiss because now you're not looking at one seam accidentally venting. You're looking at a network waking up, and networks create repeatability, and repeatability is the enemy of randomness. This is where the story gets uncomfortable again, because a network of conduits can produce patterns of thrust, tiny, almost invisible, but consistent enough to steer. So JPL ran updated orbit fits with a rotating outgassing model, the kind used for comets that push themselves with jets. Those models can soak up drift if the jets are messy, but the residuals still preferred a clean directional term, like the push had a bias that refused to average out. That is exactly what you'd expect if the activity is not scattered vents, but a line vent that fires at specific phases like a controlled bleed. Now add MIRI, Webb's mid-infrared instrument, because it can see deeper into the thermal behavior, not just surface brightness, but how heat is distributed. MIRI data hinted that the stripe wasn't only a surface skin effect, it looked like the warm region had depth, like heat was being delivered from below. Depth is a big deal because surface heating fades fast, subsurface heating holds longer, and it can feed night-side emission without sunlight in the moment. So NASA tried the most reasonable explanation, super volatiles trapped in a deep pocket, venting through a long fracture line as internal pressure finds an exit. That's plausible, and it still keeps the story natural, but it doesn't remove the fear because a deep volatile pocket is exactly how you build a long-lived thruster, even if you never meant to. Then the timing tightened again. The stripe brightened in short steps, not smooth ramps like a system shifting between states. Stepwise behavior is rare in purely thermal inertia because heat diffusion is continuous. Steps look more like thresholds being crossed. Crack opens a little, pressure drops, flow changes, crack opens more, flow changes again. That is how you get thermal steps without needing any exotic tech. But once steps exist, you can predict them, and once you can predict them, you start looking for an external trigger that decides when the steps happen. That trigger could be tidal flexing, except there is nothing nearby, large enough to flex an interstellar visitor like that in open space. So the only remaining triggers are internal stress cycles, rotation stress, pressure cycles, and the environment around it, plasma, dust, solar wind. And the environment around it is where DSN started whispering again, because timing drift anomalies clustered around the same stepping windows. Not huge drifts, not headline worthy. Just repeated, structured, like the medium got slightly warped at the exact times the stripe changed state. If you're trying to stay calm, you say it's coincidence. But coincidence dies when the pattern repeats 3 times in the same cadence. At that point, you have to consider the ugly possibility. The activity is not only venting gas, it might be interacting electrically with the surrounding plasma. Charged dust, ionized gas, magnetic coupling, these are real physics effects, and they can create feedback loops that keep a region active longer than sunlight alone would. A plasma interaction could also explain why the stripe looks clean, because electromagnetic forces can shape flows into filaments. Filaments are basically nature's way of drawing lines, and if 3i Atlas is generating a filament-like outflow along a seam, the heat signature could follow the same filament geometry like a glowing track. That would make the stripe a visible marker of an invisible structure surrounding the object, like a sheath forming and reforming in a stable alignment. Now imagine how that looks from far away. A cold object that drags a thin warm band across its night side because the space around it is doing organized work. That is not how we picture comets. So NASA widened the watchnet again. Not just Webb, but big ground infrared telescopes, not as sharp, but useful to confirm trends. They pulled data from VLT-class instruments and smaller survey facilities, looking for matching changes in brightness and coma asymmetry. And the same theme kept appearing, small asymmetries that aligned with the stripe's orientation, like the object had a preferred axis of activity. A preferred axis is poison for randomness. It suggests internal structure, a spine, a conduit, a dominant fault, something that behaves like a design even if it is accidental. And then the biggest tell arrived quietly. The stripe drifted slightly in latitude, a tiny slide across the thermal map, as if the activity migrated along the seam. Migration means the system is evolving. Comets do evolve, but they tend to degrade. They become more chaotic as surfaces break down. This looked like refinement, not decay. Refinement means the pathway is becoming more efficient, like pressure is carving the route that leaks best, turning a rough crack into a cleaner channel. So the story becomes a slow sharpening. The more we watch, the less messy it looks. And that is the opposite of what you expect from a dirty snowball. At this point, the team started using language like persistent thermal band and phase-coherent asymmetric activity, phrases that sound harmless until you translate them. Persistent means it survives. Phase-coherent means it follows a schedule. Asymmetric means it pushes in one direction. Put those together and you get the quiet sentence nobody wants to say. 3. iAtlas may have a consistent mechanism to generate directional acceleration. Not huge, not cinematic, but consistent enough to shift predictions. And once prediction shifts, you can't treat the object as a passive visitor anymore. You have to treat it like a body with agency-like behavior. Agency-like is the safest phrase because it admits the pattern without claiming intent. But you and I both know what it feels like when a pattern behaves like a plan. Because the stripe didn't just change randomly, it progressed through stages, thin, wider, kinked, doubled, stepped, migrated, like a sequence. That's a ladder, and ladders are built to go somewhere. So now the question becomes brutally simple. If the warm stripe is climbing a ladder, what is the top rung? What is the end state it is trying to reach? Now this is where the warm stripe stopped being interesting and started being operational, because the next orbit solution didn't match the old one anymore. JPL ran the numbers again after Webb's second thermal pass, and the fit improved only when they added a persistent non-gravitational term, a tiny push that wouldn't go away. That push wasn't huge, but it was stubborn, like a compass needle refusing to sit straight, and the direction lined up with the stripe's orientation far too often. You could explain one alignment as luck, two as coincidence, but by the third revision, the pattern became obvious. The heat band and the drift were talking. This is where the story gets quietly scary, because once you can connect heat to motion, the object stops being observed and starts being behaving. NASA doesn't like that word. They prefer activity. They prefer outgassing. Anything that sounds like weather instead of intention, but weather doesn't pick a clean axis and keep it. Weather doesn't repeat a phase, locked push like it's following an internal clock. So the analysts did the only sane thing. They tried to break the link by forcing the model to assume random jets, rotating, sputtering, averaging to zero. The model failed in the same way every time. The residuals preferred a consistent bias, a push that kept the same sign instead of flipping like noise. That's when the stripe became the prime suspect, because a line vent can create a net acceleration without looking like a dramatic plume. A line vent also explains why the night side stays warm, because active flow can keep the surface from cooling, and the flow doesn't need the sun in that moment. Now, here's the detail that made the room go still. The best fit push peaked when the stripe was most visible, not when the day side was brightest. That means the acceleration was tied to the seam state, not to sunlight intensity, like a valve opening and closing on schedule. At that point, NASA began treating Webb's thermal maps like telemetry, not just imagery, because the stripe was effectively a readout of a hidden system. They started asking, if the seam brightens, does the trajectory bend? And for the first time, the answer looked like yes. In a way, you could model. And when you can model it, you can forecast it. And forecasting is the moment curiosity turns into containment. So they ran forward predictions, projecting where 3i-Atlas should appear if the seam kept bleeding in the same rhythm for weeks. Then they compared that to fresh tracking from ground observatories, and the object landed closer to the seam active path than the dead rock path. That doesn't prove control, it proves influence. And influence is enough to turn a harmless visitor into a system you have to monitor like a machine. Because machines don't need to be hostile to be dangerous, they only need to be capable of changing state faster than your predictions can adapt. Now watch what happened next. NASA quietly scheduled tighter observation windows, not for pretty science, but to catch the seam during its transition steps. Webb was asked to look again at a specific rotation phase, and Alma was tasked to listen for gas lines at the same exact window, and the same story repeated. Stripe brightens. A weak molecular signature appears, orbit residuals tighten in the same direction. You can almost feel the shape of the mechanism. Pressure rises, conduit opens, flow begins, surface warms along the line, tiny push accumulates, then it relaxes. That would be normal comet physics if it were chaotic. The problem is that it's consistent enough to look engineered by nature. And once consistency exists, the scary question becomes practical. How long can the pressure supply last, and what happens when it runs low? Because if it runs low smoothly, the push fades. But if it runs low abruptly, the conduit can fail, the surface can crack wider, and the behavior can change fast. That's when comets become unpredictable, and unpredictability near big planets is how you get surprises you cannot undo. Which brings us to the next corridor, the region where the object's path intersects stronger gravitational structure, where small nudges can produce big geometry. Every trajectory has leverage points, moments where tiny changes early turn into large offsets later, and NASA started mapping those points like danger zones. The warm stripe turned those leverage points into something else, opportunities that only exist if the object can choose when to push. Because if 3i Atlas can push itself at will, even slightly, then a leverage point becomes a steering gate, a place where it can choose a new lane. And the most unsettling part is that the gates ahead were obvious. The next major encounter geometry near a giant planet was already on the board. So the internal question became simple. Is the seam warming because it's losing volatiles, or because it's preparing for a time push at the next gate? No one wrote that in a paper, but you can hear it in the way teams change cadence, more frequent updates, more cross-checks, less relaxed language. Because the story is no longer, what is it made of? The story is, what can it do, and how long before it shows us again? And Webb's warm stripe is the first time we caught a possible actuator in plain sight, glowing gently on the side that shouldn't glow at all. If you want the cleanest image in your head, imagine a flashlight under ice. Not bright enough to blind you, but bright enough to show there's a channel. A channel means direction. Direction means drift. Drift means revision. And revision is how a mystery becomes a moving target. Now the seam stopped acting like weather and started acting like a clock. Because the brightening didn't wander anymore, it returned at tighter intervals, like a metronome. JPL didn't call it a countdown in any memo, but you could see it in the schedule. Shorter prediction windows, faster orbit updates, and more eyes on the same few hours. Webb caught the stripe flaring in 3 steps again, but the pauses between steps shrank, as if the internal pressure cycle was compressing into something more urgent. ALMA confirmed the same thing in chemistry. Faint CO lines rising and falling on the same beat, like the seam was breathing out in pulses instead of leaking slowly. That matters because pulses produce direction, and direction produces leverage, especially when the object is about to cross regions where gravity turns tiny nudges into big lanes. The team at JPL started plotting gate moments, times when a small push would change the next month of sky position. Then they compared those gates to the seam's rhythm, and the overlap was ugly, because the strongest seam states lined up with the most sensitive gates, like the object's own cycle was synced to the places where steering works best. NASA's DSN added another layer. Phase drift and deep space links spiked exactly during the seam peaks, not enough to break contact, but enough to show the medium got disturbed. At that point, it stopped being one instrument's problem because timing, heat, chemistry, and trajectory were all pointing at the same axis on the same rotating body. So they tried a controlled prediction. If the seam peaks at 317 UTC, the object should drift this many milliseconds by tomorrow. And they waited for the sky to answer. The sky answered quietly because the drift landed inside the seam-driven forecast, not the passive rock forecast, like the object accepted the model and followed it anyway. And that's when the fear changes flavor, because you can live with randomness, but you can't live with something that becomes predictable in the same way a machine is predictable. Webb's next pass showed the stripe widening at one end, like the conduit was opening farther along the seam, extending the active line as if it was preparing a longer burn. Hubble saw the coma tilt slightly in the same direction, a barely there asymmetry, but stable enough that it looked less like dust chaos and more like a faint exhaust bias. None of this screams engine, but it whispers thrust, and when you're tracking an interstellar visitor, whispers are enough to rewrite maps and schedules. The official phrasing stayed calm, non-gravitational acceleration consistent with asymmetric outgassing, but the internal question was harsher: can it choose when to vent? Because if it can choose timing, it can choose where the push points, and if it can choose where the push points, then the next maneuver won't look like an accident. So the new goal became simple: catch the seam mid-transition, the exact moment it flips state, because that flip is where intent hides, even if the mechanism is natural. They coordinated Webb, ALMA, and ground scopes like a sting operation, stacking observation time on the same rotation phase, because one clean flip would settle the debate. Then the stripe did something cruel. It dimmed almost to nothing for a full cycle, like the seam went quiet, and everyone thought the pressure pocket finally collapsed. But on the very next rotation it returned brighter and tighter, a thinner line with hotter contrast, as if the system had vented, reset, and came back more efficient. That reset is exactly what you see in controlled bleed systems: purge the unstable gas, stabilize the channel, then reopen with less noise and more direction. JPL's fit tightened again, and the direction of the push rotated by a small angle, not random, but locked to the object's spin axis like the seam was re-aiming. Vera Rubin's survey data added a weird footnote. A faint companion speck appeared near the predicted corridor, too dim for drama, but too synchronized to ignore. NASA didn't claim it was a second object, they called it a background coincidence, but the speck kept matching the same relative motion on 3 separate nights. When you track an interstellar body, 3 nights of matching motion is how coincidences die, because stars don't drift with you, and random rocks don't mirror you. At the same time, DSN timing drift formed a cleaner waveform, a smooth rise and fall instead of jitter, like the environment around 3i Atlas was being shaped. Engineers hate clean waveforms because noise is normal, but clean waves mean someone found a frequency the system likes and then drove it on purpose. Webb's thermal map showed why the warm stripe developed tiny hotspots along the line, like valves or vents opening in sequence one after another, not all at once. That sequence matters, because a line firing in order creates torque, and torque can change orientation, and orientation controls where the next push points in space. And now, you can see the shape of the trap, a seam that can pulse, a body that can torque, and a trajectory headed toward the next leverage corridor in the giant planet zone. If the stripe lights up during that corridor, the maneuver won't be a tiny revision anymore. It will be a clean lane change, the kind you can't explain with just dust. And this is where it gets surgical, because NASA tries to predict the next move, and 3i Atlas answers back. So NASA tried to get ahead of it, because once you suspect a time push, you stop observing like a tourist and you start watching like security. They built a prediction window around the next leverage corridor, the stretch of space where a millimeter per second becomes a kilometer of mist later. Webb was scheduled not for beauty shots, but for continuous thermal sampling, catching the stripe before, during, and after the seam's usual peak. ALMA stacked its antennas on the same hours, listening for the faintest CO rise, because gas is the only confession a natural mechanism ever gives. JPL ran a forward model assuming the seam would pulse again. Then they asked the hardest question, what if it doesn't? What if it deliberately breaks rhythm? Because breaking rhythm is how you hide control, even if control is just a pressure system finding a smarter path through a changing crack. So they tightened tracking with ground observatories, VLT, Subaru, and every survey feed that could provide astrometry without waiting for long pipelines. And for the first time, NASA's DSN shifted into a noise audit, logging timing drift at higher resolution, like they expected the medium itself to twitch. Everything was lined up to catch the next step, and that's when 3i Atlas answered in the worst possible way. The warm stripe didn't brighten where it always brightened. It jumped to a new segment on the night side, offset by a few degrees like a reroute. Not a fade, not a smear, a relocation, as if the conduit under the surface switched exits and chose a cleaner line to vent through. Webb's map showed the old stripe cooling normally, while a fresh stripe lit up nearby, thin and hard-edged, like a line drawn over cold stone. That kind of swap is not what comet models predict, because natural fractures don't usually close cleanly and reopen in parallel with that much precision. And the new stripe wasn't alone, it came with 2 short crossbars, tiny warm cuts intersecting the main band like junctions. You can call it cracking, but cracks don't usually intersect in neat, rightish angles on a tumbling ice body unless the stress field is very organized. ALMA picked up a matching change in gas geometry, weaker overall but more collimated, like the flow tightened into a narrower stream. A narrower stream means better thrust efficiency, because you waste less energy in random spray and you get more net push per molecule. JPL's residuals responded instantly, not with a huge jump, but with a change in direction, like the push vector rotated to match the new stripe. That's the moment you feel the floor move, because a natural outgassing model should lag, but this looked almost synchronized across systems. NASA tried to blame observation cadence, but the timestamps were ugly. The thermal reroute happened first, then the drift fit improved after. Then DSN logged the cleanest anomaly yet, a short phase shift that rose and fell like a waveform, perfectly centered on the reroute moment. No solar storm was scheduled, no upstream monitor warned of a pressure wall, and yet the timing drift behaved like something local changed the path length. If you've ever watched a lens distort light, that's what it felt like in radio, as if the space near 3i Atlas briefly became a structured medium. Now, the safe explanation is plasma interaction, ionized gas, shaping itself into filaments that can focus or scatter signals in a way we don't fully map. But plasma filaments don't usually form stable junction shapes, and Webb's thermal image wasn't just a filament in space, it was warmth on a surface. So NASA ran stress models, spinning body, thermal cycling, internal pressure, and they found one mechanism that could create reroutes without magic. A deep volatile pocket feeding multiple shallow channels, where one channel seals with frost while another opens, forcing flow to jump tracks. That's plausible, and it still scares you, because it means 3i Atlas can redirect its own vents as conditions change. Redirected vents can redirect torque, and redirected torque can redirect orientation, which means the next push can be aimed even if nobody is aiming it. Webb caught a second reroute 11 hours later, smaller this time, like a micro adjustment, and the pattern began to look less like failure and more like calibration. The new stripes formed a staggered ladder, 3 parallel lines with slight offsets, as if the object was distributing heat across a set of pathways. And here's the detail nobody liked. The ladder spacing matched the pulse interval NASA had been tracking, like the geometry itself was encoding the rhythm. Hubble saw a faint asymmetry in dust that matched the ladder axis, almost like a thin fan. Not dramatic, but stable across 2 consecutive exposures. Subaru confirmed the same bias, and when 2 independent optical systems see the same tilt, you stop calling it noise and start calling it direction. JPL updated the model again, and the best fit term now preferred a piecewise push, short segments of acceleration instead of one smooth constant leak. Piecewise acceleration is exactly what you get when a system pulses, rests, pulses, and the rest periods were shrinking like the countdown was tightening. NASA attempted the cleanest test, predict the next pulse by the ladder rhythm, then schedule a snapshot precisely at the expected crest. Webb arrived on target, Alma listened, and the crest didn't happen. The seam went quiet, the gas dropped, the stripe dimmed like it refused the appointment. For a minute, that felt like relief, because random systems don't care about your schedule, but the refusal looked too tidy, like a deliberate miss. Then, 30 minutes after the window closed, the stripe flared brighter than before, not as one band, but as a full hook shape across the night side. A hook is geometry, a hook is curvature. A hook is not the straight crack logic people were clinging to, because cracks don't naturally bend that cleanly. Alma caught a sudden rise in CO at the same instant, and the line profile suggested the gas was streaming in a narrow, directed flow. JPL's residuals reacted again, and the drift term snapped into alignment with the hook's direction, like the object chose a new push vector at will. At that point, NASA's language turned colder, less activity and more event, because an event implies a trigger, not just gradual warming. The event didn't last long, but it left a signature, a new baseline shift in the orbit fit, small but permanent, like the system wrote a new chapter. And Webb's final frame of the window showed the hook cooling in sections, not evenly, but in steps, as if valves were closing one by one. That is exactly the behavior that no standard comet model is built to expect from an interstellar visitor moving this fast through this cold. So the only honest conclusion left is the one everyone tries to avoid. 3i Atlas isn't just heating, it's managing where it heats. Managing heat means managing flow, and managing flow means managing force, and force, even tiny, is how a path becomes a choice.